students, today we are going to deal with the new wave properties of the light, that is called diffraction. In the diffraction we will be considering the diffraction from a single slit, from the double slit, and the width of the central maxima that we are going to observe. Hello students, now we will study a different wave aspect of the light, that is called polarization. Now let us see what polarization is. Now what is a polarization? Now as we have seen, what is light? Light is an electromagnetic wave. Now what do we mean by an electromagnetic wave? That means a wave that is composed of electric fields and magnetic fields. So what is light? The actual picture of light is like this, that you have an electric field here, okay, and then there is a magnetic field, and that magnetic field is in this manner. So if we consider, okay, and so suppose this is x axis, this is y axis, and this is z axis. So this is the direction of the movement of wave. The red one is the electric field, and this blue one that I have drawn is the magnetic field. This is magnetic field B, this is electric field E. So actually this is the light wave. This is made up of electric field, and then there is a magnetic field, which are, and now the angle between this and this, the angle between this and this angle is 90 degree. Okay, now natural light I have shown here. This is the wave. Now what is being shown here is, this is the wave that it is going. This is the electric field that is varying like this. It's going up and down. Magnetic field is coming out of the plane of your monitor and going in. It's like this, going in and out, going in and out, which is being shown by a dot. Okay, so this is the light wave. This is an electromagnetic wave, and this is how the fields are varying. Electric field is varying. Till now we have used the expressions for electric field, right? It is this electric field which is varying, and we have shown it by equations. And this is the actual picture of a light wave. So this is parallel to the plane here, in this plane of your monitor, and this is perpendicular. So this is the representation of natural light. Now we'll see what this behavior of polarization is. Now suppose this is a string. We use a very simple experiment to show you what polarization is. A string going through a slit like this. Okay, what happens is that now you start giving it a disturbance. I start giving it a disturbance in this manner. What happens? This disturbance travels forward. Now when it is traveling forward like this, now if the slit is like this, it can easily cross that slit, because the slit is along that disturbance direction. So the direction of disturbance and the slit width, they are in the same direction, so that disturbance is able to pass through. So it can pass through this and go here and reach here. So this wave is able to pass through this slit and cross this. Okay. Now what will happen if you try to give it a disturbance like this? You try to give it a disturbance like this, the slit width is here, and you are giving a disturbance like this. Will this disturbance be able to cross this slit? You can easily see from your practical experience it won't. So it will be able to pass only when this field, the direction of this variation, this disturbance is along the slit width. If it's perpendicular to that slit width, there won't be any transfer, there won't be any transmission of waves. This is the polarization. Since light wave has an electric field that is varying in this direction, it's going like this, and there is magnetic field, we are considering the electric fields here. So if you put a slit here, it will be able to pass through. If this slit width is like this, means it's a three-dimensional like this. It won't be able to pass if it's like this, but it would be able to pass only when the slit width is like this. This is like this, and now there is a disturbance like this. So your electric field can pass, because now the disturbance is along the direction of the slit. Now this property is called the polarization. This is the polarization of light waves, that only when you have the disturbance in a particular direction that the wave can pass, otherwise it can't pass. Okay. In natural light, now let's see what happens in the natural light. Let's get a glance over it. In natural light, millions of transverse vibration occur. Now, what is transverse vibration? We have seen this is perpendicular vibration that I am talking. This is moving in this direction, velocity is in this direction. See, electric field is in this direction. Transverse, it is perpendicular, always perpendicular. Perpendicular to the direction of propagation of wave. But for convenience, we can assume the rectangular components of vibrations with one component lying on the plane of the diagram and the other in the plane to the other is perpendicular to the plane of the diagram that I had shown. Another one was this, but both are perpendicular. Light waves are electromagnetic waves with electric and magnetic fields oscillating at right angles to each other. We have seen this in the terms of diagram, and also to the direction of propagation of waves. Therefore, the light waves can be polarized. Because of this nature of having electric field in a particular direction, magnetic field perpendicular to that direction, we should have a particular direction of electric field. There is a particular direction of electric field, so we should have a particular direction of slit. Then only it can pass, otherwise it can't. Now, here I have shown this with this is a material having some interesting properties. What that property is, it only allows light along a particular direction to pass through. It cannot, it doesn't apply, allows the light in a different direction. Light in a different direction means the electric field of that light in a different direction. So we'll be, when I say the light in a direction, what I mean actually is it's the electric field. So we'll be, whenever I say, you have to understand it in the terms of electric field now, when we are discussing polarization. So what will happen? This only applies, this is the optic axis. Now what is optic axis? Optic axis is the direction which allows that direction to pass through, that direction of the light. Light means electric field. So when you are, this is, it has both the vibration, this and this. Now it has vibration like this or like this. Okay. Now when it crosses, try to cross this, it can only pass through this. This is the property of this material. And such materials are called polarizers. Okay. What it does is that it blocks this black ones that you see. It only allows the field along this direction to pass through. So what you get outside is only this purple ones. So only this electric fields pass through. These electric fields are blocked. These electric fields cannot cross through it. Now you may wonder why I am telling that both are the electric fields only. Why is that both are the electric fields? Why is it not that one is the magnetic field? There is a magnetic. What I am telling is that if you have electric field in this direction, then the magnetic field will be in this direction, perpendicular to it. If the electric field is in this direction, the magnetic field will be in this direction. Okay. But it's not always that according to your axis the electric field will be there. Electric field could be in any random direction. So what we do is that we convert the electric field. Suppose this is your x-axis, y-axis. Your electric field is somewhere in between, right? It could be anywhere. So we break it into components. One is this component, one is this component, x and y. Okay, and now it is passing through this optic axis, and it only allows this component of the electric field to pass through. Here we are not considering anything about the magnetic field. Magnetic field will always be perpendicular to that electric field component, but we are not considering that. We don't have to bother about it. So if there is an electric field, we break it into components, and only that component passes based on the polarizer optic axis. Okay. Now that once this has passed, if you again put this polarizer like this, nothing change will happen, because again it is along the same axis and all of this can pass. So it is polarized. This is a plane polarized light. Why do we call it a plane polarized light? Because the polarization is in one plane. If you consider this as a plane, so in that same plane the polarization is happening. Now consider this unpolarized light. It is going here like this. This is plane polarized light. Now what will happen if you rotate it by 90 degree? It has not been shown in the figure properly. What happens if you rotate it by 90? If you rotate it by 90, you can see what happens, that now that the vibration is in this direction and your axis will be like this when you have rotated it, no light will be able to pass through it, right? Because only the vibration in this direction could have passed through it, right? But once I have absorbed this part by passing it through this, and then you rotate this polarizer, so now it is blocking this part because you have rotated it by 90 degrees, so you get no light from here. So you can see this is a very simple, very basic property, and how it is being manifested here. In terms of electric field, when you are observing, you can see what is this polarization property that is coming into picture. So when an unpolarized light, now this is what I am discussing, I am the same thing here. When unpolarized light is incident on the polarizer, the vibrations that are parallel to the crystallographic axis, this is the optic axis, is the crystallographic axis, okay, they are transmitted, and those perpendicular to the axis are absorbed. Therefore, the transmitted light is plane polarized. Now this is also called linearly polarized because it's moving in a linear direction, straight line. So the plane which contains this crystallographic axis and vibrations is called the plane of vibration. So this plane in which it is vibrating, and obviously that optic axis is also in the same plane because that is allowing it to pass through. So they are all in the same plane. So those plane is called the plane of vibration. And the plane which is perpendicular to that, it is the plane of polarization. Okay. Now we will study an important law in this, that is called the Malus law. Okay. Now what that Malus law is, when a beam of a plane polarized light is incident on an analyzer. Now what is an analyzer? This is also the same material that is trying to analyze now, and we will see how it is analyzing. And in analyzing, what it does, it only blocks and allows. That's the property that is being used, that in some direction it will block it, in some direction it will allow it. So it's that property that is being used to analyze it. Now because we use it to analyze it, we call it analyzer. And because so we use something to polarize it. Polarize means to allow only a particular direction to pass and block all the other directions. So in that case it is called polarizer, and when you are using it for analysis, it is called analyzer. Okay. Now the intensity of the light beam from the analyzer, it varies directly as the square of the cosine. It varies in this manner. If A be the amplitude of the electric vector transmitted by the polarizer, then only the component A cos theta will be transmitted. See, it's very easy to see. Suppose this is your axis, I am drawing only one line to make the picture more clear. Suppose an electric field is there like this. This is the wave that is trying to go. This is the electric field in this direction. Now this electric field direction, obviously it's here like this, it's going like this. When it will reach here, it will be like this. Suppose this is making angle theta with the optic axis. So if it is E, what will be the component in this direction? It will be E cos theta. What will be the component perpendicular to it? E sin theta. Now what is the property of this optic axis? That it will allow the component along this direction to pass through, and it will block the other one, right? So what is the portion of this E that is crossing through this? It's only E cos theta, right? Only E cos theta goes when theta is the angle between these two. So what will be the intensity? Intensity is the square of amplitude. Amplitude is E cos theta. So the intensity is proportional to E square cos square theta. Okay. Now this intensity of transmitted light, we remove the constant of proportionality. We write it as K. So it's A cos theta square, Ka square cos square theta. Now we write Ka square as the I naught. What is the maximum velocity of maximum intensity of this? When this will be equal to 1. So that maximum intensity I call I naught. Okay, because when cos square theta is equal to 1, this will be maximum. I call that value I naught. So I put I naught for this value now, which I have given the name. So expression is this. Okay. Now let's see implications of this. Now what will happen when theta is 0 or 180? So when you put theta equal to 0, this value becomes 1. Intensity is I naught. Whenever it is 180, it will become cos theta is minus 1. This implies what is cos square theta? This is again 1. So intensity is again I naught. What will happen when theta is 90? It will be cos theta, cos 90 is 0. So what is intensity? It is 0. Okay. Now what will happen when unpolarized light is incident on the analyzer? Unpolarized. What do you mean by an unpolarized light? An unpolarized light means a light that has no definite direction of electric field. What is polarized? Means a particular direction of electric field. What is unpolarized? Means no particular direction. Means at any point electric field could be in this direction, this direction, this direction, or this direction, or this direction, or this direction. When the wave is going like this, there is no fixed direction. It could be any direction. That kind of light is called unpolarized. Now what will happen when you pass this unpolarized light through a polarizer? What will happen is that this will block all the other this random values. Only what it will allow to pass is only the one that is along this axis, and you get this light. Right? So how can you make an unpolarized light a polarized one? Simply allow it to pass through a polarizer. It will only allow those along the optic axis to pass through. It will block all of the others. So it converts them to polarized light. So when unpolarized light is incident on the analyzer, the intensity is 1/2 the intensity of incident light. Why? See, very easy. What is the average value of intensity? See, since the intensity will be changing because it has electric field along all the directions, so it's changing. Average value will be average value of I naught into average value of cos square theta. Now I naught is a constant, right? So if you have a constant value, what will be its average value? It will be the same. Now what is the average value of cos square theta? It's actually half. So that value is I naught by 2. I hope you know the finding the average value of trigonometric ratio for anything, not only trigonometry, for anything. If you have to find out the average value, suppose t, what you need to do is you have to find out, suppose you need to find out x, the average value of x when it is changing with respect to time. You find out x into dt and divide it by dt. This is the average value. This is a universal formula. This is for the average. So if you find out the average value of this, what you will have to do is cos square theta into dt by integral of dt. This will be the average value of cos square theta. Okay. So here now, sorry, here it will be d theta because it's varying with respect to theta. So you get integrated, you get the values. It comes out to be half. Now let's see an example here. Two Polaroids are oriented with their planes perpendicular to incident light. Okay, there is a light here, there is a Polaroid here. Okay, this Polaroid is coming here. Now they are oriented, the Polaroids are oriented with their planes perpendicular to incident light. Means one is this, another one also is perpendicular to the incident light. Means if you can see, this angle is 90, right? So this is what it's saying. Now you have another one which is also perpendicular, but the transmission axis make an angle of 30 degrees. So if this is one direction, another direction is this. So from the vertical, which is this direction, makes an angle of 30 degree. Okay. This is 30 degree. Now the light again, you can see that this polarizer is actually 90 degree with this, but its axis has been rotated. It's like this is the polarizer. You rotate it, this is the polarizer, the light is coming like this, it is simply rotated by theta, 30 degree from this direction, but still it is perpendicular. You can see light is coming like this, so it is perpendicular to this. Another polarizer has an axis here and the light is coming like this, so it is this kind of diagram. What fraction of the incident unpolarizing light is transmitted? What is it that you get here? What fraction of the incident light? Suppose here the intensity is I naught. Okay. This intensity is I naught. Now it is unpolarized. The light here is unpolarized, means on all the direction. So what will happen to the intensity of the unpolarized light when it comes out of this? It's I naught by 2. We saw the average value comes out because it is unpolarized. So if a light is unpolarized, means it has polarization in all the direction, what comes out is I naught by 2. Now once I naught by 2 comes, it now passes through this, which has a transmission axis 30 degree. That angle is 30 degree. So what will be the intensity now? Apply the formula. I naught is here what? I naught by 2 cos square theta. Cos theta is cos 30 square. So this is I naught by 2. Cos 30 is root 3 by 2. This is squared. So you have 3 I naught by 4. What is the fraction of the intensity? This is I. What is I by I naught? This is 3 by 4. That is 75%. So what is the intensity that has crossed this? What has come out from here? It is 75% of the intensity. Okay. So it was this I naught. Then it became I naught by 2 because it was unpolarized. It's important. We applied the formula I naught cos square theta only, but since it was varying, it was unpolarized, we got I naught by 2. That's what we did here. So after I naught by 2, now apply I naught cos square theta, where theta is 30, we get this value. Okay. So we have done the diffraction part of the light, and we have seen how the wave properties in terms of diffraction manifest itself. So for more on this, stay tuned to Ask IITians. Thank you.